All right, let's talk about empirical formula and what empirical formula is and how to do some of these problems. An empirical formula, what it is the lowest whole number ratio of subscripts that you can have in a chemical formula. So sometimes when you have a chemical formula, the subscripts in the chemical formula itself are able to be reduced by the same factor. So you can tell here that the C6H12O6, that has been divided by 6 and then it reduces down to this formula, which we call the empirical formula. So this is the one with the lowest whole number ratio for carbon, hydrogen, and oxygen for this particular formula. So to find empirical formula, the skills that you need to be good at are really just percent composition and converting between grams and moles, which are two things that we already know how to do, so that is good. And in a few of the problems, actually in lots of the problems, you're going to just be given the percent composition of elements to begin with. They'll just be stated in the problem, and that'll look a little like this. So you'll have a problem that gives you the stated percent compositions of some of these elements, like 36.48% sodium, 25.44% sulfur, and 38.08% oxygen. Based on those percents, a reasonable question is, what is the empirical formula for a compound containing these elements in these percents of composition? So the first thing you want to do with these is not so much think of these as percentages. Remember, these are all going to add up to 100%. And so what you want to do is sort of in your mind just imagine these as a number of grams. And that means we're working with, you know, a hypothetical 100-gram sample of whatever compound this is that's made from sodium, sulfur, and oxygen. So instead of thinking of those as percents, just think of them in your own mind as grams. And then that's going to allow us to transfer those grams, convert those grams into moles, which is an important part of this problem. Okay, so what that looks like is this. So here's the next step to these problems. These were given as percentages on the page I just got away from, and now I've got them as grams. Okay, and these grams we're going to divide by the molar mass of those individual elemental molar masses, and that's going to convert this number of grams of sodium into moles, grams of sulfur into moles, and grams of oxygen into moles. So we can hammer those out real quick here. 36.48 divided by... that gives us 1.587. Okay, 25.44 divided by 32.07. That gives us 0.7933. And then for oxygen, we do 38.08 divided by 16.00. And that gives us 2.380. Okay, now these numbers don't really mean a whole lot to you, and they're not going to get used in the empirical formula other than to do one more calculation, which will give us the subscripts for the empirical formula. So what you want to do now is identify which of these three numbers is the lowest of these three numbers, and it is this one right here, the 0.7933. Once you know which one is the lowest mole value, you're going to divide all three of these things by that lowest number. Okay, so put that lowest number under each of the other mole values. Okay, and then the division problem that you're about to do, all three of these division problems you're going to do, those answers are going to give you the subscripts in your empirical formula. So we can hammer these out. This first one, I'll do this one in my head. That's a 1, right? And that's always the way it works. And then let's see, 1.587 divided by 0.7933. This one is a 2. And these numbers, you'll almost always get really, really whole numbers like 2.000, like in this example. It's possible that you would get like a 1.9 or something like that. Just round that to the nearest whole number, unless it is right smack dab on like a 1.5, in which case we have to do something a little bit different. But we'll do a problem like that or talk about it here in a second. And then this last one, 2.380 divided by 0.7933, and that gives us 3.000. So that's a 3. Now these are the numbers that you care about, because these numbers represent the subscripts in your empirical formula. So the 2 is going to come down here and subscript the sodium, the 1 subscripts the sulfur, and the 3 subscripts the oxygen. And so when you put together your empirical formula, remember we put our metal first, Na, and we're going to subscript it with a 2, and then we can do this S and O together. The S does not need a subscript, it's a 1, but the 3 goes here on the oxygen. And if you're on top of your game here, you'd probably see that this compound is probably sodium sulfite, right? So that's sodium ions here, and then a sulfite ion, and that turns out to just be the empirical formula of this compound. So that's probably the easiest scenario that you'd come across, where you're given the percentages in the problem, and then you can just convert to moles, divide by the lowest number of moles, and those are your subscripts. Now it can be a little bit harder. Like here's a question that's a bit harder, and the only thing that makes this any harder is that you are responsible for finding the percent composition before you get started. And all the information is here for you to do that. It's just one more calculation you have to make. So in this question, we have 1,370.211 grams of some material. It goes through some sort of analyzing device like a spectrometer or something like that, and it shows that in that sample there are 338.44 grams of calcium, 16.44 grams of hydrogen, 202.79 grams of carbon, and 812.54 grams of oxygen. What is the empirical formula? So remember, to do empirical formula, you kind of need to start with the percent composition, which then you'll treat as grams. And so to find the percentages, all you really do is just take your part, which are these numbers here in the problem, and divide them by the total sample size. And that'll give you the percent of each of those elements in that sample of compound. So here's the work, here's what that'll look like. So we've got our calcium, hydrogen, carbon, and oxygen, and we've got their the number of grams of each element from the problem divided by the total sample size in each of these problems. And then we're going to multiply those decimals that would pop out of there by 100, and that's going to give us our percent composition, okay? And those numbers are right here. So these are the resulting percentages of those elements. 24.70% calcium, 1.200% hydrogen, 14.80% carbon, and then 59.30% oxygen. And remember, what we do from here is that we just treat those percentages as an amount of grams, which then we're going to convert using our dimensional analysis into moles, right? So let's go ahead and rack those out. 24.70 divided by the molar mass of calcium, which is 40.08. That gives us 0.6163. Okay, next one here, 1.200 divided by 1.190. Oops. Okay, next one here for carbon, 202.7 0.79 divided by, oh no, sorry, I got the wrong number here. 14.8, 14.80 divided by 12.01. That is a 1.232. And then finally down here for oxygen, we'll do the 59.30 divided by 16. And what would I do? There we go. And that's 3.706. Okay, so here we are, now we identify the lowest number of moles of these problems, and it's this one up here. So we're going to divide each of these mole values by the lowest, 0.6163, 0.6163, 0.6163, 0.6163. This one's 1. It's always a satisfying one to do. 1.190 divided by 0.6163. Okay, so that's a 1.9. I'm going to go ahead and round that up to a 2. Okay, 1.232 divided by 0.6163. That's a 1.99. That's definitely a 2. And then here we have 3.706 divided by 0.6163. And that is a 6.01. That's going to be a 6 then. Okay? So now these are the numbers that are going to be the subscripts of these elements in our empirical formula. So, I have a space here. What that means is that our calcium subscript is a 1. I'll come back and erase that here in a second. The hydrogen is a 2. The carbon is a 2. And the oxygen is a 6. Now, this is a totally fine way to write this, and I wouldn't ever mark this wrong or anything like that, but at a certain point you might start to recognize what these chemicals are actually going to be. Like if you were really on the spot and you thought about what H, C, and O could come together to make, you might remember that this is the general formula for a bicarbonate ion. And so probably what this compound really is calcium, Ca, and then HCO3 subscripted with a 2. That's like the real varsity move that, you know, I wouldn't expect you to know how to do this or whatever. But so this is a fine answer, but that's sometimes the way these end up going. Okay. So the very last thing that you would ever be asked to do about empirical formulas is to calculate, based on an empirical formula, the molecular formula. And this is just how this goes. So if a problem asks you for a molecular formula, there's a couple of things you're going to need. You're going to need the empirical formula. You're going to have to find the empirical formula. And then you're also going to need the molar mass of the compound in question, and that has to be given to you in the problem. If you don't have the molar mass in the problem, then you cannot calculate the molecular formula. Okay, so here's how that goes. Let's just say that you did all of the work of finding an empirical formula. You did all the percentage to grams, grams to moles, divide by the lowest number of moles and whatnot, and you ended up with an empirical formula of CH2O. All right, so if this is called your empirical formula, and that's something that like you calculated, you figured this out from the problem. Okay, now the problem would go on to say, now based on this molar mass, like if the compound in question if the compound has a molar mass of 240.21, then what is the molecular formula? And to do that, you basically just take the molar mass that's given in the problem and you divide it by what's called the empirical mass. And the empirical mass is the mass of this compound here, okay? So the empirical mass you find just by the same way you'd find the molar mass of a compound. You take the mass of a single carbon, 2 hydrogens, and 1 oxygen, and let's go ahead and calculate that. So that's 12.01 plus 2 times 1.008 plus 16. So the empirical weight here of our compound, our empirical formula, has a mass of 30.03. Okay, and then we're going to take the molar mass, which is given to you in the problem here, and put it as the numerator, 240.21. Okay, we're going to divide these things, and hopefully that gives us a whole number. It should. They're designed to give you a whole number answer. So let's just make sure this is going to work. So 240.21 divided by 30.03, and that gives you, 7.999. I'm going to go ahead and call that 8. And what you do with this number here is you basically just distribute it through your empirical formula. So your empirical formula from this example was this here. So CH2O. So just distribute this 2 all the way through. So 2 here, 2 here, and 2 here. And we're going to multiply the 2 by the subscripts in the empirical formula. So your final molecular formula is C2H4O. Oh, not a 2. I'm such a dummy. This is an 8, right? Sorry, this not a. I thought that sounded kind of wrong. Not a 2. Sorry. So the 8 will distribute. My bad. I don't know what I'm thinking too. So the 8 will distribute to the carbon, the hydrogen, and the oxygen. So sorry, C8H16 and O8. Okay, that's your molecular formula. Sorry for the mistaken 2 for 8, but I think that's a quick fix. Okay, so that's how you do empirical and molecular formula stuff.